see if we can get through this next part. So we'll talk about mass conservation. And what we're going to talk about is the material form of mass conservation. Who knew that there were two statements of mass conservation? There's a material form and spatial form. Right? Spatial form is the one that you're used to seeing, I'm sure. Flow in, flow out. But there's also the material form. And
gradient of density equal to
what's that? No. Let's just think about a solid. No reactions, no. Yeah. Let's just work it out, see what happens. All right. So we have a potato in the reference configuration. And we're going to deform that potato to the current configuration. And over here in the current configuration, we're going to look at a little infinitesimally small chunk of mass that we'll call dm. And in these, I'm going to be using the symbols M and V, and it's a little bit hard to tell the difference between an uppercase and a lowercase m and a V. So I'm going to put a little O. So anytime you see a little subscript O on a variable, that means it's pinned to the reference configuration. Another way to think of that is that it's taken at time t equals to t0. And so yeah, this is because we're in the reference configuration, we define the position of that guy with x, and we're going to track that through the motion, that exact same differential mass in the current configuration will be little x, will be in the position little x, and we'll call that dm. Okay. So another way to write, dmo, right? The mass of that the little differential mass would be the reference density, rho o, times dVo, right? The volume of that little differential element. Okay? Likewise, over here, dm could be written as rho, again, rho is a function of time, just to be explicit, times dV. dV. And so, if it's the same element, right? If it's the same element and mass is conserved, then dMO must equal dm, right? Or rho 0 times dV0 must equal rho of t times dV, right? Always, always. So if we write that down, we write rho 0 dV0 is equal to rho. I'm going to drop the t, but understand that's a dV. And then if we wanted to, so that was for, you know, that little differential mass. But if we wanted to track or have a statement that tracked the entire body, right, from the reference to the current configuration, we'll just call this, actually, let me use more, quit doing that. A more common symbol would perhaps be so what's an omega? So that just means the total body and the total volume of the body in the reference in the current configuration. So then if we want to track this for all time of the total body, then we'll have, we can integrate, right? And understand that whenever I write, you know, we can write a single volume integral or we can write a triple integral over line segments, right? And so if I do that, then we have like, and I'm just going to write that. Then you have dx1, dx2, dx3 equals now, does anyone remember from vector calculus how you could do a change of coordinates in an integral? Yeah, just notice like just going from this volume to that volume is just a change of coordinates, right? In the sense that I want to go from d little x to dx, right? If you remember, then what you have is like, and I'll write it, you know, dv little v is equal to the Jacobian determinant, the absolute value of the Jacobian determinant of dv0, and you know, just to be clear, then that is equal to, so this is in terms of, you know, if I write it in terms of volume, but if you go back and you look at what the volume is, right, in terms of the big X and little x, then what that is the absolute value of the determinant of partial little x I partial big X j little x I big X j times dv0. What is this? What's the partial of little x with respect to the partial of big X? Deformation gradient. So this is the determinant of f ij dv0. And so then we call this j. So then we can rewrite, we can use this now, right? So little dv is j dv0, absolute value of j dv0, right? So we can plug j dv0 in for little dv in that equation up there. So we have now the integral over omega o rho o dvo is equal to the integral omega o rho absolute value j dvo. Now this equation must hold, right? Anytime you have like an integral that's integrated over the same bounds on both sides of the equation, then what's in the integrand must be equal to each other. Has to be, right? So if it holds for the integral, it holds for what's inside the integral. So rho 0 is equal to rho times the absolute value of j, or the absolute value of j is equal to rho times Now, these are densities. Are densities ever negative by definition? Okay. So do I really need that absolute value sign? Not really. It's always a positive number. Later we'll see in computation that we'll use Jacobians there, determinants there, and later in computation, and it's like a big flag that something went wrong if you get a negative Jacobian determinant. It means you like inverted the element. Right? So J then is equal to the determinant of F, and that's equal to rho 0 times rho. That is a material form of conservation of mass. You probably never saw this before because you probably never defined F. And you never took a class where you define what F is. Right? But we have it in our pocket now. So pretty simple statement of conservation of mass. So sometimes we talk about incompressible materials. What does that mean? Density doesn't change, right? So what is this fraction? 1. So for incompressible materials, the determinant of F is equal to 1. Right? So this is incompressible. As we'll see next time, and again, we will have class Thursday here. As we'll see next time, all you have to do to get the regular form of conservation mass that you're used to is take the material time derivative of this equation. You don't need Reynolds transport theorem. You don't need like thought experiments about, I mean, we all think like in undergraduate petroleum engineering, we always derive this conservation of mass by like a thought experiment, like mass in minus mass out must equal accumulation, right? And you write down, you write down equations for what the mass in and mass out, and But in this case, I mean, this is a pretty simple argument, right? All we did was track a differential element of mass from the reference to the current configuration,